Hello everyone. Today I will present our paper titled Monaural Speech Enhancement using Intra-Spectral Recurrent Layers in the Magnitude and Phase Responses. The authors are Kondukar MD Naim and Donald S. Williamson from Department of Computer Science, Indiana University, Indiana, USA. I, Kondukar MD Naim, will present this paper in ICASP 2020. Let's begin. Speech enhancement is simply put the task of denoising the speech. For example, we are in a restaurant with our friends, there are conversation on the other table, musician is playing song, game is on the TV. All these are unwanted sound making our friendly conversation difficult to hear. Therefore, we need to remove all the unwanted sound sources and boost up the desired speech. This is the speech enhancement. Using multiple microphones or microphone array to capture sound is helpful in speech enhancement because it will include some directional information. If we consider the monaural speech, which is a single channel speech, then the task is way harder. It is like hearing by one ear. Here, our goal is to enhance the speech using a single channel. The best performing deep architecture use LSTM recurrent neural networks to model short and long temporal dependencies. But these models underutilize or sometimes ignore the spectral level dependencies. Incorporating the spectral level dependencies will benefit the task of monaural speech enhancement. We can do that by a deep learning architecture that leverages both temporal and spectral dependencies within the magnitude and phase responses. Now, I will talk about a few previous works on speech enhancement. There have been many works done in signal approximation. Notably mentions the 2014 paper of Flex Weringer et al., where they find that in LSTM networks, signal approximation performs better than mass approximation. Santiago Pascal et al. Proposed speech enhancement generative adversarial network SIGAN in 2017. From then, end-to-end waveform enhancement has been tried quite a bit. In 2018, Suji Wei Fu et al. Performed or proposed a fully convolutional network which uses optimization in utterance level. Now, few papers emphasize the need of utilizing spectral information. In 2015, paper of Xinia Li et al. Used two stacked LSTM modules, one for frequency involving information and another for temporal information in the speech recognition task. In 2019, Zhen Deng et al. Proposed the time frequency LSTM, which is overlapping LSTM modules of time directional LSTM and frequency directional LSTM. They use this model for audio registration. For signal channel speech enhancement, we feel the need of incorporating the spectral level dependencies. In our prior work in 2019, we, Naim and Williamson proposed an intra-spectral layer to incorporate spectral level dependencies. However, in that paper, we consider only the magnitude responses. Now, as our proposed approach, we propose an intra-spectral recurrent layer as an output layer that captures frequency dependencies within each time frame at a speech signal. This intra-spectral layer will capture the across frequency involving information of the current time frame. For this purpose, first we train a base LSTM network to predict both the spectral magnitude responses and group delay, where the LSTM module captures temporal correlations. Then we introduce Markovian recurrent connections in the output layer to capture spectral dependencies within the magnitude and phase responses. We do this by applying our proposed intra-spectral output layer. Time for the background and notation. In the time domain, noisy speech MT is a sum of clean speech and noise. In the time frequency domain, time frequency noisy speech M is the multiplication of magnitude and exponent of its phase. We can consider this noisy speech as a union of two sound sources, STK, which is the clean speech, and NTK, which is the noise in time frequency. Therefore, we want to approximate clean speech STK hat by learning the function f phi on noisy speech. In other words, on magnitude and phase of the noisy speech. This can be close approximate to the magnitude and phase responses of clean speech and noise, given that we can separate the sound sources. Group delay of a signal can be computed as angular exponent of phase difference between k plus 1 and kth frequency. The question is, why do we need group delay? Unlike magnitude response, the phase of a speech does not show a clear structure. As you can see in the following pictures, the left one is a magnitude spectrogram of a signal and the middle one is a phase of that signal. Even though this is a clean speech signal, the phase plot does not show any clear structure. On the other hand, the rightmost picture, which is a group delay of the signal, shows a learnable pattern in log magnitude formulation. Now, we can model a deep architecture to learn the magnitude and group delay in the time frequency domain. For learning magnitude, the optimal estimated magnitude loss function, LMAG, is the sum of mean square error of magnitude between clean and estimated speech and between noise and estimated noise. For learning group delay, optimal group delay loss function will be LGD, is the sum of cosine distance of group delay between clean and estimated speech and between noise and estimated noise. Therefore, the combined loss function LMAG plus GD is the weighted average of LMAG and LGD. With the loss function, we train the baseline LSTM model. Here, clean speech and noise are considered as two separate sound sources. So each of the signal has their own magnitude and phase or group delay. LSTM model takes magnitude of the mixture and the group delay of the mixture as input. There are in time frequency domain. The output layer is branched into two ways. One is for magnitude approximation and another is for group delay approximation of both speech and noise. Since we have two separate sound sources, clean signal and noise, there are 4 outputs in total. We use a very naive deep architecture because our goal is to show the effectiveness from the incorporation of spectral information. It's important to return to phase since we train our model by group delay. For that, first we estimate the phase difference between the enhanced speech and noise delta, mod of angular difference of two sound sources. This can be written as a arc cosine function too. Then the sign of each time frequency unit is calculated by the following equation. This sign GTK can be either -1 or +1 and computed by a maximization equation of cosine function. We denote it as 1. From the trigonometric property of group delay, sources phase can have a limited set of signs GTK to form the mixture phase theta. This gives equation 2. Now, using dynamic programming within each time frame, we can solve the equation 1 and 2. Thus, we get the optimal sign sequence and phase of each sources in each time frequency unit. Now, we want to focus how recurrent networks are underutilizing the spectral level dependencies. A time unrolled recurrent network predicts ith time frame condition on the frequency component of the I-1th time frame. From the recurrent network's point of view, the goal is to capture the temporal inference, which is varying over time. The structure or relation across time is learned through this model. Now, the spectral influence can be captured using a frequency unrolled recurrent network. However, this approach is not natural because it uses future frequency points to make the inference. It means to calculate a frequency point of the current time, it infers from the frequency point which are yet to come. In human ear, we sense frequency through the vibration of the basilarity membrane, where the root area perceives high frequency and apex area perceives low frequency components. This means human frequency perception is localized and frequencies of the same timestamps are correlated. So this suggests that a frequency components of the ith time depend on its neighbor frequency component of the same time. Bearing that in mind, we propose intra-spectral bidirectional recurrent layer, ISBR layer. Each neuron of the ISBR layer represents a frequency bin of the signal. The rightmost neuron represents the lower frequency component, the leftmost neuron represents the higher frequency component. From left to right, high to low frequencies are modeled, and right to left, the high to low frequencies are modeled. The intra-spectral recurrence go both increasing and decreasing direction along the frequency axis. The red connections represent the increasing or low to high frequency recurrence, and the purple connections represent the decreasing or high to low frequency recurrence. We show the mathematical expression of the recurrence and calculation in the ISBR layer here. Delta is the vector of activations based on the input from the prior LSTM layer, and R is the weight matrix, beta is the bias vector. W denotes the weight of the connection between frequency node, sigma R the activation function for the feed forward and recurrent path. LSTM network is first pre-trained, then a ISBR output layer replaces the original output layer. LSTM network learns the temporal dependencies and ISBR learns spectral dependencies. Now, dataset. We train the model with IEEE mail single speaker data corpus. We evaluate the model using IEEE mail data corpus with 720 utterances and TIMIT, which is a multiple speaker speech corpus with 6,300 utterances. 4 speech types are used. They are signal, shape, noise, SSN, cafeteria, factory, and babel. We train and validate the network in 3 SNR levels, -3, 0, and 3 dB. Total training signals are 60,000, which is around 500 hours. Sorry, 50 hours. The total validation signals are 13,200, which is around 11 hours. We test the model with 2 additional SNR levels, -6 and 6 dB. Total testing signals are 22,000, which is around 18.3 hours. Now, experimental setup. The baseline LSTM model is with single LSTM layer with 256 units and a time distributed layer with 321 units. 4 separate output layers are used for each target. Rayleigh activation function is used for 2 output layers that predict the magnitude spectrogram. Linear activation function is used in the dense layer and for group TLA prediction. Adam optimizer group is used and early stopping is on the validation set are used. The LSTM ISBR model, which is named ISBR short, trained with LSTM network. Output layer of the LSTM network is replaced by ISBR layer and the model is retrained. Here we show the performance of our models. In the table, we compare our model with 5 other approaches. Comparison metrics are PESC, S2I, scale invariant SDR. We compare for both single speaker and multi-speaker cases. Mixture is the original noise space. L-stack approach is proposed by Deng et al. LFT is proposed by Lee et al. LISBR is our prior work with only magnitude loss function. LSTAC and LFT use a separate frequency LSTM module and LISBR uses the ISBR layer. We use the magnitude loss function for these 3 approaches. LSTM MAC plus GD is the baseline LSTM model with magnitude and group delay loss function. ISBR MAC plus GD is our proposed approach with magnitude and group delay loss function. PCTFM MAC plus phase is proposed by Lee and Kang, which use a time frequency mask incorporating magnitude and phase. PSM, MAC and phase is proposed by Erdogan with a phase sensitive mask for both magnitude and phase. As you can see, our proposed approach performs best or ties with the best results. On the right hand side figure, we show that the PES score for the seen, unseen, and overall SNR conditions for IEEE corpus. Here, ISBR, MAC plus group delay performs considerably best compared to the other approaches. Now, in the conclusion, our approach performs the time frequency masking approach, which indicates in this, our approach outperforms the time frequency masking approaches, which indicates that incorporating spectral level magnitude and phase dependencies are beneficial. We use the ISBR layer with a naive LSTM approach to show how it can improve the overall performance. The proposed ISBR layer can be used as an output layer on top of any state-of-art model. Only the first order Markovian assumption considered in the ISBR layer. We should explore higher order spectral dependencies along with sub-band spectral dependencies in a single time frame. We add recurrent with neighbor frequency component, the immediate lower and higher component, except for the highest and lowest frequency component. We should investigate if intra-spectral dependencies exist in sub-band level. And that takes the conclusion of my presentation. Thank you all. Please feel free to ask me any question if you want. Thank you.